Okay, so we are talking about the string of alpha string, which is a so this is the collection of all string sigma star, and then sigma 0 is basically our epsilon empty string. So, no occurrence of the input alphabet, and this is the input alphabet, this is the sigma square, this is sigma square means 2 times, like if sigma is a b c, then sigma star sigma 0 is epsilon, then sigma 1 is this one a b c, then sigma 2 is all the string of length 2. So, a b a c, so all the string of length 2. So, this is sigma 3, then sigma 2, sigma 3 like this. So, this set sigma star is the set of all possible string of any length including the length 0. And now we define the language, and this sigma plus is we are just not allowing the empty string. So, this is the set of all possible string which is having at least one symbol in that string, and this star is including the empty string. So, star is nothing but we can have a 0 occurrence also, the empty string and the string of any length including 0. So, that is our sigma star. And now we define the language. So, language is any subset of sigma star is called language. It is basically a collection of some strings. So, any subset of sigma is defined as a language of the language for languages. So, it is denoted by L. L is a subset of sigma star. Any subset of sigma star is called a language over sigma. Over the input alphabet sigma. So, it contains the it can be 0 string also, I mean null string also. So, language is the some set of string, it could be infinite also, but this is finite. The language, this could be infinite number of string, I mean length could be infinite, but it is coming from finite symbol, finite input symbol. So, input symbol is finite, but it could be infinite string also. So, now we will take some example of languages. Example of suppose our sigma is 0 1 binary alphabet. This set is always finite. Okay. Our input alphabet is always finite, but a string could be, we can think of infinite string. Okay. So, we can define a language like this, language of all string. So, language is a collection of strings basically. So, here alphabet is 0 1 is a collection of string, anything could be a language. So, this is a language 0 0 0 1 1 1 1, this is a language, this is a subset of sigma star. So, any collection of string is a language. So, now we will take some example of a language which is having some properties like language of all strings consisting of n zeros followed by n ones for some n greater than equal to 0. Okay. So, this we have to understand. So, we defined a language like this. So, we know the language is a collection of the string. Now, what is the property of the string? The property is it should followed by it should have n zeros, then the followed by n ones. So, number of zeros, number of ones are same, I mean not. So, like it should say 1 0 1 1, this is belongs to L, 2 0 then 2 1, this is also belongs to L, 3 zeros 3 ones, this is also belongs to L, 4 zeros 4 ones, this is also belongs to like this, and no zeros no ones, that is our empty string. So, this is our L. This is our L. So, this in short we can write it is 0 to the power n, 1 to the power n greater than equal to 0. So, this is the string of this form, 0 to the power n, we have n zeros followed by n ones, and n could be 0 also, that means no occurrence of this. So, this is also a subset of sigma star. So, any subset of sigma star is a language. This is an example of a language. Now, we will take other example like set of all string. We defined a language such that it is a string where number of zeros and number of ones are same. We count the number of zeros and we count the number of ones, these are same. So, this is second example 2 of language is another example. So, our language is our sigma is 0 1 binary input. So, binary input, and our language is say set of string, set of all possible strings of zeros and ones, I mean zeros, this is coming from zeros on, zeros and ones with equal number of each, equal number of each. That means, we have equal number of zeros and equal numbers of ones. So, those strings if we put in a bag, that bag is our L, the language. This is the way we are defining the language. So, this is consist of null, that means no number of zeros, number of ones are both zeros, no zeros, no ones. So, that is the null string, and we have 0 1, 1 0, then 0 0 1 1, in any of these places it could be like 0 1 0 1. So, number of zeros, number of ones must be same, we do not bother about. So, any combination of, so there are 2 zeros, 2 ones, any linear permutation of this will be, the 1 1 could be here, 1 1 could be there, like this. So, this way. So, this is the another example of this. Another example could be like this, we can have a string which is prime number. So, we have these are binary, we convert into decimal. So, that should be a prime number. Set of all possible string of 0 ones, zeros and ones, whose value is a prime number, 0 and 1, whose value is a prime number. So, here the null string will not come, because it has to be a number. So, for example, if you take 0 1, 0 1 is value is 1. So, 1 is a prime. So, this is a prime. If you take 1 0, this is 2, this is not a prime. Sometimes people say 2 is the even prime, but here we are defining the prime as the which is divisible by 1 and itself, but sometimes 2, but yeah, 0 1 1 0 1 0 2 is treated to be a prime, because 2 is also 2 is the only even prime. Okay. And then say 1 0 1, 1 0 1 is nothing but, or 1 1, if we have 1 1, 1 1 is 2 plus 1 3, this is also a prime. Then 1 0 0, 1 0 0 is 4, 4 is not a prime, because 4 has a factor 2. Then 1 0 1, 1 0 1 is 4 plus 1 5, it is a prime number. So, this is an example, I mean the value should be a prime. So, this is nothing but consists of, so all the sequence of 0 1s where value is a prime, like we have 1 0, 1 0 1, 1 1, 1 1 1, 1 1 means what? This is 4 plus 2 plus 1, 7, 7 is a prime number. 1 0 1 1, 1 0 1 1 means this is 8 plus 2, 10 plus 1, 11, 11 is a prime number. Prime number means which is having a factor which is divided by itself or 1. So, this set is our language. So, this is a set of all string which is, so this we can write like this, set of all string coming from this, such that W is a, when you convert W in binary, I mean integer, then it is a prime number. W has, W is a prime number in value. Okay. So, that is the meaning of that. And the phi, phi is the empty language. So, it is empty language. Empty language, but phi is not same as epsilon. Epsilon is a language of length 0, but phi is no input is there, it is an empty language, because phi is also a subset of sigma star. Any subset of sigma star is a language. So, phi is also a language. Phi is language means empty language, but if we say L is equal to this, so this is a language, this is a language consists of empty string. So, these two are not same. So, phi is not equal to this. So, phi is empty and this is consist of a language, this is consist of a string with 0 occurrence. So, these two are different, we have to be little careful about this. So, this means the no string, and this means one string with 0 input. With length 0. So, empty string, one string with length 0. So, these two are not same. Okay. So, this we have to define. So, now we will talk about something on this some problem based on this which can be handled by a finite automata. So, before that let us just talk about this language. So, as you said, language which is denoted by L, which is a subset of sigma star. So, this may contain, because sigma star is a collection of all possible string of any length starting from 0 length to infinite number of length. So, this contain this may contain an infinite number of string. infinite number of string, but the string consists of the symbol, input symbol, that is finite. String which is coming from, strings are drawn from, this is important, our input symbol is finite, but we can make it infinite string of length from one fixed finite input set, input alphabet set, and that is our sigma. The sigma is finite, but this is infinite, this length could be infinite. Okay. So, now we will talk about some problems like decision problems, like we have given a integer, given a 0 1 string, and we want to know whether this is a prime number or not, this type of problem. So, this is called decision problem. So, we will talk about the types of problem like decision problem, which can be handled by the deterministic finite automata. So, there could be another types of problem. This problem is called decision problems. Okay. It is basically a membership of a language. Suppose we have a sigma, which is the input alphabet symbol, and then we defined a language which is a subset of this. Okay. So, the problem L means given a string W from this, decide whether or not W belongs to L or not, whether or not W belongs to L. Okay. So, this is the, that means we need to decide. So, given a problem, so this is say for example, if we want to do the primality testing, that means given an integer, we have to decide this is prime or not. So, we will work on this on one example, which is called primality testing. Yes or no, basically. Primality testing. So, what is the problem? Problem is we have given an integer, then decide whether this is prime or not, whether it is prime or not. Okay. So, what we can do? We can express this in terms of, we can express the problem by the language, express the problem by the language LP, this is prime, consisting of all binary string consists of all binary strings whose value is a prime, binary string whose value is a prime number. So, that we are defining as LP. So, LP is nothing but the set of all string whose value is binary, whose value is a prime number. So, now we have a given a W. So, which is a 0 on string which is coming from sigma star. Now, we have to output, our machine should output yes if W belongs to LP, no if W does not belongs to LP. So, this is the decision problem, yes or no. So, we just output this. So, we have to model in such a way such that we have to have a finite automata such that it will accept only those strings which is having whose value is W, whose value is a prime number. So, which belongs to LP. So, this is a decision problem. So, this type of problem we will handle by the help of DFA. Now, we will see how the DFA processes a string. So far we know the DFA is processing on a input alphabet. Now, we will try to understand how the DFA is processing on the string. How a deterministic finite automata processing a string. Okay. So, we have a DFA which is consists of 5 tuple. This is the finite set, this is the sigma which is the input, delta q0 f, this is our DFA. Now, suppose we have a string consists of this A1, A2, say AN. This is a string where these AIs are coming from sigma. Now, we will see how a DFA processes on a string. We know the DFA is processing on a DFA is the, so this delta is defined to be a so it is a rule, we are in current state, we take a input alphabet, it will be in the next step. So, now here, but if we are having a string, so how we will process? So, basically we have a, so we start from a q0 which is the starting state, then we have the input, we just keep on reading this, we put it into the tape and we keep on reading this. We first read A1. So, A1 means, so it will be some another state q1. So, say it is q1. So, q1 is nothing but, I will just erase this. Okay, so q1 is, so we have to start with q0 and our first alphabet is, so this is q1. A1. Now, we are at q1, our second alphabet is A2. So, we read A2, suppose it is going to q2. So, q2 is delta of q1 A2 like this. So, this way we continue. So, dot 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 dot. So, at the, so we continue like this. So, q3 it will go to A3, it will go to q3 like this. So, finally, we are at q, say qn minus 1 and then we read an and suppose it is going to qn. Okay. So, this is, so qn minus 1 is delta of qn minus 2 an minus 1 and then at the end q n will come from q n minus 1 after q n. This sum of the q may be same, we do not know, but to write this as this way. Okay. Now, so it is reached to a state q n. Now, if q n is, so after reading this symbol a 1 a 2 a n, so we just read, we start from q 0, we keep on reading this and we are changing the state based on the rule delta, and at the end suppose it is reaching to the state q n. Now, if it is the final state, if q n is final state, then we say this string is accepted by the DFA. If this, then we say this W is accepted by the DFA. Okay. So, this is the meaning of the accepting by a DFA. We have given a string, we start with the starting state and then we change the state based on the input alphabet, and after the end of the string, like the last symbol is a n. So, after a n we reach to some state that is q n. Now, if it is happen to be q n to be a final state, then we say this our DFA is accepting this, or if it is not, if the q n is not in, then we say W is rejected. So, either it will accept or it will reject. When it will accepting, if it is reaching to a final state at the end of this execution of these symbols, because our delta is not on the string input, delta is on the alphabet input, but string is consist of the alphabet. So, we keep on changing the state, reading the string, and finally, if we reach to a final state which is the accepting state, then we say the string is accepted by our DFA. If it is not a final state, then we say the string is not accepted by our DFA. So, that is the rejected string. So, we will continue this on more details. Thank you.